All right, very good. So welcome to this next masterclass. We're working through the Cambridge International Examinations A2 papers for chemistry. And in this masterclass, we're looking at paper 5, which is all about your ability as a student, not so much to know a lot of chemistry, but to be able to work with a lot of chemistry, your planning, your analysis and evaluation of experiments in chemistry. There's 2 questions, and as usual, what we'll try and do is we'll try and work through these, but particularly pick up the points that the examiner raised where the students had the most challenges, and spend most of our time working on the areas that the examiner found that the students were weakest. Okay, very good. So in this first question, the context, if we can just we can't highlight that, can we? Okay, let me do that. The context is there's a solution here, and we know the approximate concentration. It's measured in grams per decimeter cubed. And so the whole intent of this piece of work is to move from knowing approximately what this concentration is to knowing it accurately. And that's what the whole question is about. And during the work in the question, we're going to do a titration, which will give us that exact value for the concentration, rather than just knowing this approximate value that we have at the start. And this is a bit tough, I think, because the first question that we get into here, the examiner said in the examiner's report that almost all students found this first step one of the hardest steps. So it's not as if the examiner's being nice to you and giving you something nice and easy to start with, straight in there on something that a lot of students found difficult to do. But what I'll do then is we'll just spend a little bit of time on this, because actually there's a fail-proof way of getting these half equations written down. And if you know what the way is, you get them 100% every time. So let's just look at what that fail-proof way is. And you've got to spot that when you're working out these equations, well, these half equations, aren't they? These half equations, that everything's happening in acid solution. And this fail-proof method that I'm just going to talk you through is correct and always works if you're working in acid solution. All right, it won't work if you're working in alkaline solution. Right, so just bear that in mind. That's the only qualification really about this. And to be even nastier to you, the examiner in the question is giving you that first and that second, even though when you do the work, this one is easier and that one is harder. So not only has the examiner launched you into the hardest question, but instead of giving a question which gives you the easy part first, he's giving you the hardest part first. So this is a tough start to the paper, but we're going to start by looking at this one, which is easiest. And we've got to write half equations for oxidation and a half equation for reduction. And so the way that you do that, if I take this one here, is that you write on the left-hand side the reactant, and of course on the right-hand side you write the product. Okay, pretty obvious starting point. And your next step is to say, well, what is the oxidation state of the manganese, or the oxidation number? Now, pretty obviously the oxidation number over there is 2 plus 2, because the manganese has a manganate ion of 2 plus. Over here, you just have to know that oxygen normally has an oxidation number of -2. And so the oxidation number of the manganese there is +7, because the -2 of the oxygen, you've got 4 of those, and the +7 of the manganese gives you an overall negative charge there. So these are the oxidation numbers. And the oxidation number is going down. And if the oxidation number is going down, that is a reduction. And that makes sense because the examiner told us that up there. And you know from your mnemonic, oxidation is loss, reduction is gain, that If it's a reduction, then the electrons are being gained. Reduction is gain, electrons are being gained. So if electrons are being gained, your first step is to put them on the left-hand side. They're being gained. So we wrote down the oxidation numbers, and then we put on either the left or the right side of the equation. If electrons are gained, they go there. If they're lost, they go on the right-hand side. The next step is to balance oxygens with water, right? Because this is all in solution, isn't it? It's an aqueous solution. We're allowed to put water into this equation. And you can see there's 4 oxygens over here. How are we going to balance that with water? Well, we're going to have water over here, and we're going to have 4 lots of water because we need 4 oxygens, yes? So we balance the oxygen with water, and then we balance hydrogen atoms with H+. And that's why I told you you had to make sure this was in acid solution, because this is way of working only works with acid solution. So we balance the oxygens there, and now we've got a problem because we just added 8 hydrogens. So to balance those, we're going to put 8 hydrogen ions over here. And at that point, you can see that we've got a balanced equation in terms of the atoms. And the next part is that you've got to balance charges, because it has to be the same charge on the left-hand side and the same charge on the right-hand side. On the right-hand side, there's a charge overall of 2+. On the left-hand side, we can't, that doesn't add up to 2 at the moment, 2+. But if I have 1 negative charge there and 5 negative charges there, and that's 6 negative charges, 8 positive charges overall. On the left-hand side, it's got a 2 positive charge overall. Overall, on the right-hand side, there's a 2 positive charge as well. So that's all done, and as a final check, you just need to check that the number of electrons that we ended up with by balancing the charges is represented by the change in oxidation number. You can see I've gone from a +7 oxidation number to a +2 oxidation number, and to do that, there's a gain, reduction is gain, a gain of 5 electrons. So that all makes sense. So our first half equation, the reduction, is the manganate 7 plus 5 electrons plus the 8 hydrogen ions, and that's going to manganese 2 plus and 4 H2O. All right, so that was the easy one. Now we've got this harder one to do here, but the thing is, if you follow the method here, then it all falls out easily. So let's just work through that. Now, back to the pen. So we've got these ions here, haven't we? And that's on the left-hand side. And on the right-hand side, we've got carbon dioxide. And the first step is we've got to write down the oxidation number of carbon. Well, the oxidation number of oxygen usually is -2. This has no overall charge. So the oxidation number of carbon must be +4. And then if you go over here, the oxidation number of oxygen is normally -2. The oxidation number of hydrogen is normally +1. And so that must mean that the oxidation number of carbon is +2 to give me an overall charge of -1. So the oxidation number of carbon is going from +2 to +4. The oxidation number is going up. If an oxidation number is going up, that's an oxidation. And that's correct, isn't it? Because the examiner is saying up here it's the oxidation of this iron to carbon dioxide. So that looks good already. And we know from our mnemonic, oil rig, we used that already, didn't we? Reduction is gain. The oil part means oxidation is loss, all right? So electrons must be being lost in this process. There's electron lost, which means they're going to be appearing on the right-hand side of the equation. So that's got us quite a long way. And now we've got to go through these steps here, haven't we? So the first step, balance oxygen. Now, do we need to do that on this occasion? There's 2 oxygens here, 2 oxygens here. We don't need to do that step on this occasion. Then we have to balance the hydrogen with H+, but we've got 1 hydrogen atom over here, none over here. We can put a hydrogen atom over here. And then we've got to balance the charges. Overall here, there's a negative charge. So to get a negative charge over here, we need to have 2 electrons. 2 negative charges from the electrons plus 1 positive charge means there's an overall negative charge on the right-hand side. There's an overall negative charge on the left-hand side. So that's been through our steps. And then finally, we do a check. The oxidation number went from +2 to +4. That's an oxidation. It's a loss of electrons. How many electrons have we lost? Well, it looks like we should lose 2 according to the oxidation numbers, and that's what we've got in our equation there. So that little bit of a method of writing out the equation, writing out the oxidation numbers, balancing with water for oxygens, balancing with hydrogen ions for hydrogen, balancing the charges, and then checking is a fail-proof way of making sure you get these 2 half equations written out. And it doesn't seem that difficult, really, that method, but the examiner is saying that most students failed to get these 2 half equations right at the start of the paper. Okay, good. Next part then. All right, so we had up here, we had this approximate concentration, if you remember, up here, approximate concentration in grams per decimeter cubed. The question is now asking us to calculate that concentration, not in grams per decimeter cubed, but moles per decimeter cubed. And so you've got to work out for, what was the substance here? It is magnesium methanoate, isn't it? It's that. So you've got magnesium, and then you've got this methanoate ion, and you've got 2 of those. So the way that I worked that out was I've got here the relative atomic masses. So for magnesium, I've got a relative atomic mass of 24.3, and then I worked out the relative atomic mass of this methanoate anion as 45. So I just added those up from these relative atomic masses there. And then because I've got 2 of those, then the relative formula mass of all of that comes to 2 lots of 45, which is 90. And if I add those all together, I end up with that as my relative formula mass for magnesium methanoate. But we've got to go from a concentration in grams per decimeter cubed to moles per decimeter cubed. And we know, don't we, that we've got how many grams? We've got 150 grams in a decimeter cubed. So our mass is 150 grams. And to work out the number of moles, the amount, that is always the mass divided by the molar mass. So our mass is 150 grams. And our molar mass is just this relative formula mass in units of grams per mole. So that's 114.3 grams per mole. I do that calculation and I work out a concentration of 1.312 moles per decimeter cubed. Okay, that gave us that one gave us the number of moles, the amount in 1 decimeter cubed. And this is a little bit tricky because the examiner is asking for the concentration of magnesium methanoate that we got there, and then the concentration of the methanoate ions. And you just have to spot that when you have magnesium methanoate and you dissolve it in water, well, you get 1 magnesium ion, but can you see that 2 down there? You're going to get 2 methanoate ions. And so if the concentration of magnesium methanoate is that, the concentration of the methanoate ions is going to be twice that. So the concentration of these methanoate ions is going to be twice that, which is just multiplied by 2, 2.624 in the units, because we want the units moles per decimeter cubed. And remember that these, well, because they're derived from the approximate concentration earlier on, they're still approximate concentrations. And the whole purpose of the experiment we're doing is to move from approximate concentrations to accurate concentrations. Okay, now if you look here, these are actually really, really concentrated. That's 2 moles per decimeter cubed. That's almost 3 moles per decimeter cubed. It's very, very concentrated. And so they're saying as you go through this experiment, you're going to need a diluted solution, because at the moment our approximate concentration is showing us that the concentration is really too concentrated for us to work with. So we've got to show how we're going to take that concentrated solution and dilute it. And so there's a number of steps here. I'm surprised the examiner's only giving 2 marks. There's lots of things you can do. The first step is you're going to take either a 5 centimeter cubed bulb pipette. I'll explain what that is in a moment. Or, it doesn't matter which one you use, or a 10 centimeter cubed graduated pipette. Now, my writing's not great and my drawing is even worse, but I'll try and draw what those things look like. Okay, so this bulb pipette is something like this. You might have seen these in the laboratory. So it has a bulb in there, a long tube, like this. This is a bulb pipette. Okay. And you can draw up the liquid into that bulb, and it has a little line up here. And when your meniscus, that's the shape of the water surface, is just touching the line, then the volume that you've got in this whole pipette and its bulb is 5 centimeters cubed. So that's the bulb pipette, and you're filling it up, or you're drawing or sucking up the liquid to that mark there. And when the bottom of the meniscus is at that mark, you've got exactly 5 centimeters cubed. That's the bulb pipette. The graduated pipette is like this. It's a long... Can I start again? I'm trying to draw a straight line here. So it's like this, a long glass tube, like that, no bulb in it this time. And it'll have measurements on the side like this, going all the way up to 10 centimeters cubed. All right. The bulb pipette had a line there at exactly 5 centimeters cubed. And again, you're going to draw up liquid into this, and you're going to draw up a liquid until you get to the graduation on the side here that says 5 centimeters cubed. And your liquid will just have its bottom of its meniscus against the 5 centimeter cube graduation. So it doesn't really matter which one of those you use, either the bulb pipette or the graduated pipette, but you've got to use something that's giving you a very, very accurate value for 5 centimeters cubed. If you said, oh, I used a measuring cylinder, one of these things that you see in the lab here with a base at the bottom, things like that, those measuring cylinders aren't sufficiently accurate. You've got to have one of these much more accurate ways of measuring a volume. So you're going to have this bulb pipette or graduated pipette of the magnesium methanoate, because we're wanting to dilute that, aren't we? So we need to do that. And then the second step is, once you've measured the 5 centimeters cubed, you're going to add it, the 5 centimeters cubed of magnesium methanoate, you're going to add that volume to a 250 centimeter cubed called a volumetric flask. Volumetric flask. Just get my pen to work. And if you saw one of those in the lab, it would have a long, thin neck like this and a great kind of bulb at the bottom where most of the volume goes, and then a thin neck. And it has a little mark on it there. And when you fill that up to the mark, then you've filled up exactly 250 centimeters cubed. So what you do is you take the liquid that you measured here, or the liquid you measured here, and you put that into the flask. It'll just be a little bit of liquid down the bottom there. And then you fill the rest of this up with deionized water. Deionized water. And you fill it up very, very carefully until your meniscus just reaches that mark there. And then you know that the 5 centimeters cubed has now been made up to 250 centimeters cubed. You put a stopper in, and then you turn the flask upside down a few times to make sure it's really mixed. And because you took 5 centimeters cubed and you diluted it, or you made it up to a volume of 250 centimeters cubed, you have made a solution that is 50 times more dilute. So those were the 2 points the examiner was looking for, that you're using a bulb pipette or a graduated pipette, and you're adding deionized water to 250 centimeter cube volumetric flask, and you're making it up to the mark. In some other exam papers, it wasn't marked here, I've seen the examiner require that students add a stopper to the flask. Because if you don't add a stopper, what's going to happen over time in a nice warm laboratory is the water will evaporate from here, and you'll end up with a more concentrated solution because the water has evaporated. So I think you're adding a stopper and mixing, and then leaving the stopper in place once you've done that dilution. And actually what you do in the lab is you put a sticker on here as well, because if you're busy in the lab, it's very easy to forget what you've done in which flask. So put a sticker on there. That's just a top tip if you're working in the lab. They weren't marking it here, but later on you'll have to write on there the exact concentration of the magnesium methanoate solution that you determined in this titration. But for the purposes of this equation, the examiner is just checking you're using these pipettes mark in a 250 centimeter cubed volumetric flask. Good, so we've done a bit of work in the lab here. We're just about to carry out the titration, and it says, well, we've got to add some sulfuric acid. And, well, do we have to really be concerned about the volume of sulfuric acid that we need? Well, kind of yes and no. If you look back to the equations up here, you've got to make sure, haven't you, that you've got enough acid. If we don't have enough acid, then we won't get a complete titration of the methanoate ions here. So you've just got to make sure that you've got enough acid added, or you sometimes abbreviate that to say excess. I've got excess acid. So the answer the examiner was looking for down here, because you've got 2 points, is the volume of acid is only important to make sure the acid is in excess, or there's enough acid. Yes? So that was the one mark the examiner was looking for. The second mark, of course, was that the reaction requires acid as well. You can see that when we balanced the equation earlier on, even under acid condition, the reaction requires the hydrogen ions, doesn't it? It requires acid. Okay, good. So that's we've diluted the magnesium methanoate. We've got the acid ready to add. Now we need to know, when we're doing the titration, what we're looking for as the endpoint. Now, often in titrations, you can add an indicator, can't you? So you can see the exact point at which you reach an endpoint. There's no real indicator here So the examiner is just asking, well, what would you see so that you know that you've reached the end point of this titration? And the trick is that you're adding manganate 7, aren't you? And it's oxidizing the methanoate ions, and the manganate 7 is being used up and converted to manganate 2. Now this, the point here is that this is deep purple. That's the color of the manganate 7, really, really deep purple. And this, well, it's strictly speaking, it is pale pink. And it's so dilute that for most practical purposes, you can think of that as colorless. And the magnesium methanoate solution as well is colorless too. So what happens is that as you add this manganate 7, as it goes into the solution, the deep purple color completely disappears because it's getting used up to make this pale pink or this colorless manganese 2 ion over here. And you've reached the end point because when you add 1 drop too much of this, it's such a deep purple color, the single drop that you've added to reach the end point of the titration colors the whole solution a very pale pink. And so the answer here is, well, you're looking for a pale pink color. You saw that in the mark scheme. And you could say, well, that's because this has been formed. Well, in practice, that's not really the case. That's so dilute that it appears colorless. The pale pink color that you see is because you just added 1 drop of this too much. And that deep purple color, when it's in slight excess, as it is when you've just got to the end point, is pale pink. So that's why you're getting a pale pink color there. All right, so the examiner is now being a little bit kinder to you because we had to work out the equation earlier on, and actually there was a stoichiometry, or a ratio of the number of moles of 1 to 2.5. And if we didn't work that out from the redox half equations, then we're getting told it now. So we've got a stoichiometry of manganate 7 to the methanoate of 1 to 2.5. And so we've got to use this information to calculate the concentration of this, because if you remember, that was approximate, wasn't it? We're now trying to work out an accurate concentration of the methanoate ions. And we know that we had a volume of 25 centimeters cubed of that, and the volume that we measured in the titration was 25.5 centimeters cubed of the manganate. And we know, don't we, that the concentration of the manganate was exactly known. So we knew the concentration there was 0.0200 moles per decimeter cubed. And we're trying to find out the concentration here, and we're trying to find out the accurate concentration there. Well, you're going to be using the formula that the concentration is the number of moles, or the amount, divided by the volume. Now you've got volume and concentration there, so you can work out amount, because amount is just concentration times volume. That's easy stuff, but you just have to watch it, don't you? Because the concentration is in moles per decimeter cubed, but the volume is in centimeters cubed. So you've just got to do a conversion factor to make sure you're always working in the same units. So the amount is 25.5 times the concentration, but divided by 1,000, so we're working within the same set of units. And if you do that, you end up with a concentration, you end up with an amount here, the number of moles, of 5.1 times 10 to the minus 4 moles. Yeah? Because you're working with that formula there for concentration, and you rearrange it to make the amount, or the number of moles, the subject to the subject to the equation. You put in the numbers, you use the 1,000 conversion factor, and you ended up with this as the number of moles in 25.5 centimeters cubed of manganate 7. Now, the examiner told us that the stoichiometry is 1 to 2.5. So if the number of moles there is 5.1, to calculate the number of moles here, you're just multiplying up, aren't you, by 2.5. Yes? So our number of moles over here is, you do that multiplication, 1.275 times 10 to the minus 5. And now, because we've got an amount, the number of moles, and because we've got a volume, then we can work out concentration, can't we? Concentration is the amount divided by the volume. And so you just have to do that calculation in here, which is 1.275 times 10 to the minus 3. And you're going to multiply, and that's the amount, isn't it, there? And that's the volume, which is 25 centimeters cubed. But we've got to multiply that by 1,000 because we're moving from centimeters cubed to decimeters cubed. And if you do that calculation, then the value that you're looking for, which is this concentration here is 0.0, I think when you do it on the calculator, it works out as that, doesn't it? Yes. But if you look here, how many significant figures have you got here? You've got 1, 2, you've got 3 significant figures there, and you've got 1, 2, 3, you've got 4 significant figures here. So your answer should be to the smallest number of significant figures that you had in the question. And so we got our answer here. So I think that should be, isn't that right? To 3 significant figures. So just so we're absolutely clear about that, we just say 3 significant figures there. Good, so now we've worked out, haven't we, this is now, we have an accurate concentration, because we started off with the approximate concentration, and all that work that we've done has helped us calculate an accurate concentration for the methanoate ions. But we're not finished, because if you remember, right back up here, scroll all the way back up, where was it? Right up here, the approximate concentration was that. And we went through this step, didn't we, of doing a dilution here, all right? We did a dilution by 50. That was a 50-fold dilution. So to actually work back to the real accurate concentration of the solution that we first started with, well, we've got now the concentration of these methanoate ions, and we calculated that just up here as 0.0510 moles per decimeter cubed. And to get back, because we had a 50-fold dilution, the original solution must have been 50 times more concentrated. So we're trying to get back to our original solution, so we've got to multiply by 50, which gives us a concentration of 2.55 moles per decimeter cubed. But if you remember that magnesium methanoate has 2 of these methanoate ions for each formula unit. So actually the concentration of the magnesium methanoate, excuse me, is actually going to be half that concentration, because that concentration was just the concentration of the methanoate ions. And the concentration of this formula unit here is half of the concentration of methanoate ions. So you've got to go multiply by 50, haven't you? And then you've got to divide by 2. And that gives you a concentration of 1.275 moles per decimeter cubed. All right. Now, you've got to work here for 3 significant figures. You can see here when we did the calculation, it came out as that. And you know that when you're doing your rounding, if it's below a 5, you round down. And if it's 5 or above, you're rounding up. So this gets rounded up to a concentration of 1.28 moles per decimeter cubed. And that's the answer the examiner is looking for there. Good. So that was all the work that you had to do to work out not the approximate concentration, but now the accurate concentration. So we've done all our hard work, and now we've got a bit more thinking to do. And the examiner is asking us about, well, the solubility of this magnesium methanoate. You can determine that at higher temperatures. We just determined it at room temperature, didn't we? So there's only 1 mark up for grabs here. But you've got to think about an experiment, how you determine the concentration. How does that vary with temperature? Okay, so you're trying to link, well, as the temperature increases, what happens to the concentration? And you've got to say, well, which of those is an independent variable and which is a dependent variable? The independent variable is the one that you can change. And so it's much, much easier, isn't it, to change the temperature at which you do a reaction, the concentration. And actually all the work that you did up here was all about calculating and measuring concentrations. So the thing that you're free to change is the temperature. So that's the independent variable, and the one that's going to be dependent on the temperature is going to be the concentration. Now most students got that according to the examiner. Some students didn't get that. They were saying other things like the volume that you measured in the titration or the solubility of the magnesium methanoate. But really the clues are all in the question if you read it carefully, because the experiment is to determine how the concentration is affected by the temperature. So the 2 variables are actually in the question, aren't they? You shouldn't get that wrong. It's only 1 mark there. Now, when they do this experiment, what happens is that the solubility or the concentration increases with temperature. And they've given us this little equilibrium here. Now, if the solubility increases with temperature, that must mean that this equilibrium is then moving toward the products, because the solubility increases with temperature. More of this dissolves as the temperature increases. Equilibrium is being shifted to the right. And that must mean that if the temperature is going up and the equilibrium is shifting to the right, then the enthalpy change for this reaction must be endothermic. So you've got to say, this is, well, normally it says state and explain. It just says explain here. So the enthalpy change is endothermic or positive. You could use Le Chatelier's principle. And the Le Chatelier's principle is that for any system at equilibrium, the system will change to minimize the effect of any change put upon it. Now, what change did we put upon it here? We tried to increase the temperature. And so this system moves to minimize the effect of the change that we put upon the equilibrium. And if this is endothermic, then even though we increase the temperature, this reaction will try to move to reduce the temperature, and it does that by having an endothermic reaction. So you're quoting Le Chatelier's principle, that in this case, as the temperature increases, then products are favored because the reaction is endothermic. And you should be quoting Le Chatelier's principle at that point. Now, strangely enough, the examiner said that a lot of students really struggled on this. And what the examiner's testing here, kind of secretly, is that you should know the laboratory test for sulfate ions. So this is one of the tests that you should know. For example, you should know the test for chloride ions or the test for bromide ions. These are all tests that you should know. And the test for sulfate ions is that you add barium chloride. And barium chloride is barium 2+ and Cl-. And when you add barium chloride, and if the solution you're testing contains sulfate, then those two combine together to give you a precipitate of white barium sulfate. So the thing that you should know from your A-level studies is that to test for the sulfate ion, you add barium chloride, and it immediately gives you a white precipitate of barium sulfate. So barium sulfate is highly insoluble because you can use it in this laboratory test. So you know that, that's something that you know from your A-level studies, and then saying, well, okay, we're doing this experiment again, we're not going to use magnesium methanoate, we're going to use barium methanoate. But what happens if you add sulfuric acid to barium methanoate? Well, this reaction is not going to work anymore because the barium in barium methanoate is going to react with the sulfate from the sulfuric acid, and instead of providing acidification of the solution, allowing you to do a titration, you're going to get precipitate of white barium sulfate, and that precipitate will interfere with the titration. So you can see here the examiner's kind of expecting you to know this test and then apply it here. And you can see that if you start having white precipitates being formed in a flask where you're doing a titration, you're not going to be able to do that titration accurately. Good. Okay, so that's the end of question 1. Change gears now, and we're looking at the second question. Only 2 questions in this paper. And you've got this equilibrium happening here. And on this occasion, the examiner is giving you an easy mark to begin with. The examiner was giving you a tough, hard mark to begin with on the first question. Second question is being a bit easier for you. And the equilibrium constant that expressed in terms of concentrations is you have the concentration of the product. Remember, these square brackets mean concentration. And because you've got a stoichiometry of 2 there, you put the product concentration to the power of its stoichiometry. And then on the denominator here, you have these 2 reactants. You've got the concentration of hydrogen. The stoichiometric coefficient is 1, so the indice is 1. And then you've got the concentration of iodine. Again, the stoichiometric coefficient is 1, the indice is 1. And I reckon that's pretty easy mark that you get there for doing the equilibrium constant based on concentration. Now, this next step here, examiner is saying that almost all students got this wrong. So again, a bit like we did in the first question, we're going to just talk through an absolutely fail-proof way of working with these kinds of questions. And the way that you should work with these is something that's called an equilibrium table. We'll see what that is in a moment. And there's a funny little mnemonic for that, which is ICE. Okay, we'll see what that means in a moment. So really, what this question is focusing on is, can you draw up an equilibrium table using these ICE principles? And what it is this. So here's our equation. And this ICE stands for initial, change, and equilibrium. Okay, ICE. All right. And it says, well, the starting concentration of iodine and hydrogen was A. So this is the starting concentration or the initial concentration. So you've got the initial concentration is A, the initial concentration is A, and at the start, because you've just got hydrogen and iodine, the initial concentration of hydrogen iodide is 0. Nothing's happened yet because you just had those as a starting concentration, and later on they reacted to make hydrogen iodide. Now, then it tells you, well, what changed during the process of the reaction? Well, what changed was that the examiner tells you that 2 Y, moles per decimeter cubed of hydrogen iodide, were changed. So that was the change in the reaction. And so the change for hydrogen and the change for hydrogen and the change for hydrogen and the change for iodine, can you see there's a stoichiometry of 2, 1, 1 there? So you got 2Y made of that. And so minus Y was the change of hydrogen, and minus Y was the change of iodine. So that's the C in this isomnemonic, what changed. And then at equilibrium, well, there was 2Y mole per decimeter cubed of hydrogen iodide. And because you started with A and minus Y moles of that reacted, then the concentration at equilibrium is A minus Y for hydrogen and A minus Y for iodine. And that way of setting out your understanding of an equilibrium is called an equilibrium table, because you've got columns like this, you see what I mean? And you've got rows. I'll go across there. So it looks a bit like a table if you drew the columns and the rows. And you have, the first column is your initial concentrations, the second column is what changes, and the third, sorry, the rows. The initial row is what you start with, the second row is what changed, and the third row is the equilibrium concentrations. So you then have to say, now that you've worked, you've got to write your equilibrium constant in terms of A and Y. Well, you knew from before, because you had the equilibrium constant, that hydrogen iodide squared over hydrogen and iodine. You wrote that out in step 1. And now all you're going to do is plug in the values for the concentration at equilibrium that you determined there. So the equilibrium constant is the hydrogen iodide concentration squared, which is 2Y squared, isn't it? And then divided by the hydrogen concentration, which is A minus Y, divided by the iodine concentration, which is A minus Y. And then you can just clean that up a bit. And so your value for Kc is 2Y squared, which is 4Y squared. And at the bottom, you've got A minus Y times A minus Y, which is A minus Y squared. And that's the formula that the examiner is looking for. So write Kc in terms of A and Y. Well, we've done that there. And we got that by putting one of these little equilibrium tables together and working through the initial, the change, and the equilibrium concentrations. Now, the examiner's being sort of nice to you here and is saying you can take that expression there, and with a bit of rearranging, you can rewrite it so that it's that. I mean, those two equations are equivalent. They've just been rewritten. There, Kc is the subject of the equation. Here, Y is subject to the equation. It's just a different way of rewriting them. Same thing. Then they do an experiment. In this experiment, they're mixing the hydrogen and iodine. They're taking air out of the flask, and you've got a particular temperature. And you're measuring the equilibrium concentration of iodine, which is that, isn't it? A minus Y, yes? And so they give you the results from this experiment, and you've got this little calculation to do here, and you've got to fill in all the values down here, and you do that, don't you, by subtracting that value from that value. And you can look at all those values in the mark scheme. And of course, say if you subtracted that from that, you end up on your calculator with 0.45. But the examiner is saying, like even though the calculator says 0.45, you're expressing this to 3 decimal places. So the examiner is seeing that you put a 0.50 at that point. And then, for example, if you come down to this one here, put that in the calculator, you've got 1.000 minus 0.200. The calculator gives you that, but actually, because you're doing the 3 decimal places, you've got to make sure you include 3 decimal places each time. And so the examiner was just saying that some students lost marks here, not because they couldn't work out the number, you just put that in the calculator, is because they didn't do 3 decimal places. So make sure you do that. Okay, now you've got to do some plotting of a graph here. And again, this is much easier for you than it is for me with this funny computer pen. But I just want to look at a couple of points on the graph here. So let's look at this point here. Okay, you're going to be plotting, aren't you? 1 on the x-axis and 0.8 on the y-axis. So that's quite nice. Can I expand this? Oh yes, there we go. Oh, cool. Good. Fantastic. All right, so you've got 1 on the x-axis here, and then you've got to find 0.8 on the y-axis. Now, each of those is 0.1, isn't it? So that's 0.1, that's 0.2, and that large line there is 0.75, and 0.8 is that line there. Do you agree? Have you got that? And so the examiner is expecting you to draw across exactly where those 2 lines meet. And if your cross or your dot isn't exactly where that line from 1 meets that line for 0.8, then you don't get your mark, or you lose a mark. So you know where these lines are drawn, you're being expected to put your pencil mark exactly where the line from the y-axis meets the line from the red axis. So that point there was 1.000, 0.800. Okay. Now the next point I'm going to look at is there's a point further along here, somewhere down over here, and the x value is 1.100, and no, my mistake. I'm trying to read off my notes here. The x value is 1.500, and the y value is 1.350. Now, finding that, the x value is quite easy. You can see 1.5 is there, don't you? Just there. So we're going to be somewhere up this thick major graph line here. But 1.35 is a little bit more problematic because you've got 1 there. If you count up here, that 1 there, we can expand it even more. That's 1.3, isn't it? I'm sorry, no, this is even more complicated. So this value here is why does that happen to me every time? So that's I can't even work out why that's happening because I don't draw those lines. Okay, so the other value is 1.135. That's the point I'm looking at. Okay, so let me go back here. All right, so drawing that one was easy. We can find 1.5, it's there, it's that thick line. Finding 1.135 is harder because that's 1.1 there, isn't it? There. And then up here, that one there is 1.2. And so that one there, well, what's that? That's in between 1.1 and 1.2. What's that? That's in there, that line, that one there is 1.15. And we've got to do 1.135, which is just a little bit less, isn't it, than 1.15. So on that occasion, the examiner is saying that you've got a 1.10 line, there it is, and you've got a 1.15 line, there it is, but your value is in between, it's 1.135. So that point, when it's plotted, getting really large here, is coming up this line here, that's 1.1, that's 1.15, And your cross is got to be in between those, you see, not on either line, but actually just there. All right, so some are easy, like this one here, because the cross is exactly on the line. Other ones, the cross is between two lines. And the examiner is being very tough on you here, because if your point isn't on a line when it should be, or it isn't between the lines when it should be, you're losing a mark. All right, so there's some very accurate plotting that's expected here. Okay, let me see if I can get back to normal size here. So that was the point there the examiner was looking for. And when you've done all your points, then you draw a line of best fit. So again, it's quite difficult for me to draw the points here, but you end up with various points, and then you're going to draw a line of best fit. And you know, don't you, that when this x-axis is 0, the x-axis represents, well, what does the x-axis represent? The x-axis represents, actually, what does it represent? Come on, let's scroll down. Have I got this back to? Okay, so that's the concentration of hydrogen or iodine. So, and you know, this isn't scrolling for me today. You know, if the hydrogen concentration is 0 or the iodine concentration is 0, nothing happens. No reaction happens. And so there will be no reaction happening. And so this value on the y will also be 0. So that's actually a kind of bonus point, a known point, because you know when one of these reactant concentrations is 0, then no reaction happens. And so there's a point at 0, 0 of the origin. And that's important because you know from your maths that the equation of a straight line is y equals mx plus c, and c, what's c, is the y-intercept, isn't it? And on this occasion, the intercept must be 0, because if the concentration of the reactants is 0, no reaction happens. So that's a kind of clue that the equation of the line that you've drawn here is actually of the form y equals mx, because the intercept c is 0. Okay, so that's just a reason for making sure you've got the 0, 0 point in there. Now, you've got to work out the gradient or the slope of your graph. And your trick for doing this is that you've drawn your line of best fit, and you've got to choose 2 points on the line that are widely separated to give you coordinates to calculate the gradient. So what you should do is you should choose one easy coordinate. And so an easy coordinate might be a coordinate on a thick line here, so a coordinate there or a coordinate there. And then your second coordinate, again, is going to be an easy coordinate on the x-axis. You might choose that one there. Okay, so these coordinates on the x-axis are easy to read. The coordinates on the y-axis are harder to read. But there's no point in making yourself life difficult for yourself by choosing a difficult coordinate on the x and a difficult coordinate on the y. So when I did this, I ended up with an easy coordinate on the x. I chose 2, and I chose 4.5. I chose that thick line there, and I chose that thick line there for my coordinates. So those were easy to read off, though I couldn't get those wrong at all. And then what you must do is you must read the y-coordinate off the graph. Now, it's so easy to go back to this table here, isn't it? And say, well, here's a set of coordinates, I'll just use those. and here's another set of coordinates. I've just used those. But those points are scattered, and you drew the line of best fit through the scatter. And so when you come to the coordinates here, the examiner was deducting points if students used these coordinates rather than coordinates that they'd read off the line of best fit. So for me, I went up the easy value here, it's a thick line, and read off a coordinate on the y-axis. And I went up here, it's an easy value, and I read the coordinate on the x-axis. Excuse my drawing. And I ended up with x-coordinate of that, y-coordinate, and I ended up with a y-coordinate of that over there. And then I was able to work out delta y by subtracting that, and I was able to work out delta x by subtracting that, and when I had delta y and delta x, I had, well, the difference in the y is 3.55 minus 1.6 for me, and 4.5 minus 2 for me. You will have had different values. They won't be the same as mine, but and I ended up with 1.95 divided by 2.5. So that's the values that I got, and the value for the gradient, or the slope, I worked out from my calculation there as 0.78. Now, you'll have a similar value for the gradient, although your calculation might be different. But the trick of using an easy value for the x and reading off a hard value for y saves you time, because you don't have a hard value for x and a hard value for y. And finally, the examiner needs this at 3 significant figures, so I need to have a 0 there for me. Now, going back to the thing we spotted earlier, you know you had a straight line, you drew that, and you know the equation for a straight line is y equals mx plus c, but we spotted, didn't we, that the y-intercept was actually 0. So the equation for our line is simplified here, y equals mx. And if we look back at the equation in B, we go back to there, where's that? There, we've got that. Okay, that's the equation. We know we've got to use that, and we have y equals a times the square root of the equilibrium constant over 2 plus the square root of the equilibrium constant. Now, if you look carefully, that's the equation of a straight line, y equals mx, and that's the same as saying y equals ma, isn't it, this time, because a is our x value, if you see what I mean. And so you could rearrange that equation to say, well, if a is the sort of x in this formula, then all of the rest of it here is the m. Do you see what I mean? So you've got y is equal to the square root of the equilibrium constant over 2 plus the equilibrium constant times a, because that's the same as saying y equals m times x, where a is what we have on the x-axis, and m, you see, the gradient is the equilibrium constant over 2 plus, sorry, the square root of the equilibrium constant plus 2. I'll try and say that again. The gradient, m, is the square root of the equilibrium constant divided by 2 plus the equilibrium constant. Now, we've got to calculate the equilibrium constant, haven't we? So we've got to make Kc the subject of the equation again. So we've got to do a bit of rearranging here. If I multiply both sides by that, I then get m is 2 plus the square root of k is equal to the square root of k. And so I have 2m plus mk equals k. I'm sort of rearranging here. And if I rearrange that, let me work on this. I subtracted k, the square root of k from both sides. This is all maths here. So therefore, the square root of k is 1 minus m. So the square root of k is equal to 2m over 1 minus m. Yes? Now, because you worked out the slope over here, you can substitute in my case, 0.780 into all of this. So I've got 2 times 0.780 over 1 minus 0.780. And if I work all that out, I end up with 7, in my case, 0.709. But that's for the square root of k. So to get k on its own, to move from a square root to k, I'm squaring what I did to one side of the equation, I must do to the other side of the equation. I'm now squaring 7.09, and I end up with a value for the equilibrium constant of 50.2. Now, you might have got slightly different values because your gradient might have been slightly different to mine. It won't be wildly off, but that process of spotting that the equation that we had in B mapped against y equals mx plus c. C is 0, y equals mx, m is the root, square root of k over 2 plus the square root of k. You rearrange, you make k the subject of the equation, and you end up with a value down here. Now, that, again, the examiner said the students found that difficult. I think if you're studying maths, that probably is pretty easy stuff to do. If you're not studying maths, then that's harder. It's just, actually, at that point, there's not really much chemistry going on, there's a lot of maths going on. So if you're a maths student, then that's it. That's good marks for you. And I think if you're not a maths student, you're probably working quite hard to get your 2 marks there. All right, now, earlier on, it said that when this experiment was carried out, they removed air from the flask, and you've got to explain why for 1 mark. Well, you've got hydrogen in there, haven't you? And the iodine as well. And air, of course, is 21% oxygen. And you're doing this experiment at 760 Kelvin. That's what is that? That's 487 degrees Celsius. And that mixture of hydrogen gas and oxygen gas at a high temperature is explosive. All right, so you've just got a very combustible mixture here. It's explosive, and you're at a high temperature. Well, you don't want too many explosions, so you've got to make sure that you remove the oxygen, remove the air from the flask. And so for the 1 mark there, the examiner is expecting you to see both a high temperature and the explosive mixture is the reason that you're removing air from the flask. You've got to have both of those to get your full point, 1 mark there. Okay, carrying on down here, the student is going to repeat the whole experiment, not in a flask of 1 decimeter cubed, but a flask of 500 centimeters cubed. So what's happening is if you put the same amount, not in 1 decimeter cubed, but 500 centimeters cubed, then the concentration, what's happened to the concentration? It's increased, isn't it? You're putting the same amount in a smaller volume. The concentration of hydrogen and the concentration of iodine have all increased. Now, what does the effect of increasing the concentration have on the rate? And what does the value, what effect does the concentration have on the value of Kc? Well, this is just a kind of GCSE knowledge or prior knowledge, isn't it? That if the concentration goes up, then the rate will increase. That's just normal work on rate of reactions. Increase the concentration, increase the rate. So that's 1 mark there. But Kc is only affected by temperature. The temperature will change a value of Kc. Otherwise, Kc is a constant. It's not changed by anything. So, you know, it's called a constant for a reason. And things like pressure or concentration don't change the value of the constant, Kc. Only temperature will change the value of an equilibrium constant. So the effect on the rate of reaction was the rate went up, but the effect on Kc was no change. Because we've changed the concentration, that affects the rate, but it doesn't affect that constant, the equilibrium constant. So you had to get both of those for your 2 marks there. All right, so now it's telling you that this reaction here is exothermic. It's got a negative value for the enthalpy change. And you're increasing the temperature from 760 to 1000 K. So what would be the effect? Well, if you increase the temperature of a exothermic reaction, then the position of equilibrium shifts back towards the reactants. That's just an application of Le Chatelier's principle. And, well, now this Kc is going to change. Because remember, the only thing that changes the value of Kc is the temperature. And we've got the position of equilibrium shifting to the left. And you should know that when Kc is about 1, then you've got, this is just a rule of thumb, you've got equal concentrations roughly of reactant and products. If you've got much more product than reactant, then Kc is greater than 1. And if you've got a lot more reactant, then Kc is less than 1. So you can see that as you have more and more reactants, the Kc value decreases. Or if you have more and more product, the Kc value increases. And because on this occasion, the value of Kc is going to change because we're changing the temperature and we're forming more reactant, then the value of Kc decreases as the temperature increases. And the examiner is expecting 1 mark there. But that rule of thumb is quite helpful for equilibrium constants, that as you have more reactants, the equilibrium constant goes down. And as you have more product, the equilibrium constant goes up. And typically when you've got about equal amounts of reactant and product, then the equilibrium constant is usually about 1. It's just a kind of rule of thumb that can help you with that kind of question. All right, very good. So that paper had 2 experiments to work through, looking at your planning, analysis, and valuation. Quite a short paper, only an hour and 15 minutes. We've tried to highlight the things that the examiner identified that students needed particular attention to. And if you've got any more questions about that paper, then the Z coaches are very, very happy to speak further with you on the Slack channel. It'd be great if you've got any questions, we can follow up there. And in the meantime, thank you for joining this masterclass, and I wish you every success in your studies of chemistry.